You ever look at a massive skyscraper, a super complex engine, or even just the phone in your hand and wonder, how did they build that so perfectly, starting from just a flat drawing? Well, the secret is this incredible universal language of drawing called orthographic projection. So let's dive in and crack the code. Here's the game plan for this explainer. We're going to start with why we even need this system in the first place. Then we'll use a really cool glass box analogy to see how it works. We'll check out the two major dialects of this language, break it down to its absolute basics, a single point, then build that up to lines, and finally, see how it all comes together to create, well, everything around us. All right, let's kick things off with the fundamental challenge. We live and breathe in 3 dimensions, length, width, height. But when we want to design something or build something, we almost always have to start on a flat 2D surface, like a screen or a sheet of paper. So how on earth do we bridge that gap? I mean, really think about it. How do you communicate every single curve, angle, and hole of a complex object with absolutely zero room for error? If I just describe a part to you and you try to make it, will it be what I imagined? Almost definitely not. That little bit of confusion, that ambiguity, is where mistakes happen, projects get delayed, and costs just skyrocket. And that's where technical drawing comes in. It's the hero of our story. To build anything with accuracy, you need a blueprint. This isn't about being artistic, it's about pure mathematical precision. We need a system to map a 3D object onto a 2D surface so flawlessly that anyone, anywhere can look at it and build the exact same thing. So the solution to this whole 3D to 2D problem is actually incredibly elegant. It's a system called orthographic projection, and trust me, the best way to get it is to imagine a simple glass box. Okay, so picture 2 huge, clear sheets of glass that cross each other perfectly at a right angle. The one standing up we'll call the vertical plane, or VP. The one lying flat is the horizontal plane, or HP. Think of these as our drawing canvases. Now, let's put our object right there in the middle of those planes. If you're standing directly in front of it, looking straight ahead, the shadow it casts on that vertical plane behind it, that's the front view. Every point gets projected straight back. Okay, now imagine you're hovering right over the top of the object, looking straight down. The shadow it casts on the horizontal plane below it, that's our top view. Simple as that. Every point travels straight down. So we have these 2 perfect 2D views, but they're still kind of floating in this imaginary 3D space. The last step is the real stroke of genius. To get them onto one flat piece of paper, we just unfold the box. And there it is. The horizontal plane just rotates down 90 degrees, and all of a sudden we have our 2D drawing. The front view is sitting perfectly aligned right above the top view. And just by looking at these 2 flat views together, our brains can completely rebuild the 3D object. That's the magic right there. Now, here's where it gets a little interesting. While that whole unfolding box idea is universal, the world is kind of split on how the box actually unfolds. This gives us 2 main systems, or you could think of them as 2 dialects of the same language. Take a look. The key difference is right there on the screen. On the left, you've got the first angle system, which is standard in Europe and most of Asia. See how the top view is placed underneath the front view? Now look at the right. That's the third angle system, used in North America. Here, the top view is above the front view. It's the same object, same views, just a different layout rule. So you're probably asking, why the difference? Well, it's all about your point of view. With first angle, you imagine the object is between you and the paper. You're projecting the image through the object onto the plane behind it. But with third angle, the plane is transparent and it's between you and the object. A lot of people find this way more intuitive. It's like you're just tracing the object's shape onto a window. That one little change in perspective is what flips the whole drawing layout. To really, truly master this language, we have to go all the way back to the beginning. The simplest thing you can possibly draw isn't some complex block. It's just a single point in space. Let's learn the alphabet before we start writing sentences. Okay, check this out. We've got a single point, let's call it A, just floating there in the first quadrant. That means it's above the floor and in front of the wall. Its projection on the front wall, the front view, we label with a little dash, so A prime. Its projection on the floor, the top view, is just A. Now, when we unfold our box, the front view A prime is above that center line, and the top view A is below it. Simple, right? But what happens if we move that point? Let's put it in the second quadrant. So it's still above the floor, but now it's behind the wall. The views get projected in the same way, but watch what happens when we unfold the box now. Because of how the planes have to rotate, boom, both the front view and the top view end up above the reference line. The drawing itself tells you where the point is. And finally, let's jump to the third quadrant. Now we're below the floor and behind the wall. The pattern flips again. When we unfold it, the top view C is above the line and the front view C' is below it. See, every single quadrant has its own unique signature on the 2D paper. Once you get this code for a single point, you can find any feature on any object. Okay, so this is cool. Once you can place 1 point, you can obviously place 2 points. And what happens when you connect 2 points? You get a line. We've just gone from letters of the alphabet to building our very first words. Now, a simple line can actually get pretty complex, fast. It can be parallel to the floor, angled to the wall, perpendicular to one plane, inclined to both, and each and every one of those orientations creates a totally unique drawing. It's like a fun little puzzle to solve every time. All right, this next idea is absolutely critical. It's called true length. Just think about this for a second. If you hold a pencil out and tilt it away from you, it looks shorter, doesn't it? Well, the exact same thing happens in these drawings. We only see a line's real, true length in a drawing if that line is perfectly parallel to our view. If it's tilted at all, the line on the paper will look shorter than it is in real life. And that leads us right to the next key idea, true inclination. It's the same principle. You can only see the real angle a line makes with a floor or a wall if you're looking at that line in its true length. If the line looks foreshortened, the angle you see is distorted too. Getting true length and true inclination right is basically the whole ballgame in engineering. So, we've gone from the big picture problem to the glass box, from tiny points to lines, from distorted views to true views. Let's tie it all together. You know, this isn't just some abstract drawing exercise. This system, this is the fundamental grammar of how we make things. Every single curve on your car, every hole drilled in an airplane's wing, every tiny circuit on a microchip, it was all first defined and communicated using these very principles. It's the silent universal language that lets a designer in one country talk perfectly to a manufacturer on the other side of the planet. We've just unlocked the basic blueprint for turning any idea in your head into a concrete 2D plan. This language gives you the power to describe anything you can imagine with perfect, unmistakable clarity. So, the only real question left is, now that you know the language, what will you create?